One. Thank you for the opportunity given to me in order to present this lecture. Today, we are going to see a few concepts in crystallography. The concepts presented here are very important and would help us solve a lot of problems in fundamental physics, chemistry, and college level crystallography. First, we'll see actually what is the influence of structure and crystals in the various fields of physics and chemistry and nanoscience that we are exploring and coming in contact with in day-to-day science today. What are the things which we have to understand, and how are these things helpful and applicable in modern day science? The variation of electronic property in solids is one of the most important concepts in crystallography, and based on various types of crystals and how electrons are distributed in these crystals, it gives us a lot of information about the materials which we study, whether it be metals, non-metals, semiconductors, any kind of material. The electronic properties actually define the overall strength, robustness, and the structure of these materials, and it is very important to understand them. For example, if we are talking about very advanced materials like Josephson junctions or superconductors, electron phonon interactions and surface electronic properties define very critically their behavior, and also electron adsorbate interactions are extremely important. For example, if we have a superconducting wire and if we have organic impurities, how these two things are interacting plays a very vital role in how electron or current is transported or even internet is transported in these superconducting wires. For example, electron spin plays a very important role if we are studying mesoscopic structures. If we are studying more advanced structures like Bose-Einstein condensates, highly correlated systems like Thorless energy become extremely important, or even in certain kinds of superconductors. And why are these things important? Because each of the electronic structure of these materials play a vital role in modern day applications like batteries and electroplating, for example. The surface of a battery is extremely important and sensitive, and today we see a lot of different kinds of anode and cathode materials, and the electronic structure and wave at these materials determine what kind of electrical charge, what kind of electrical capacity, what is the recycling capacity of these materials are defined. And again, the new materials have a different kind of electronic structure and band gap. And if we have to understand the complete the C structure and signature of these materials, the electronic influence is of extreme importance. For example, if we have an anode surface and if we are depositing a new material on this anode surface and the electronic structure of the new material or the adsorbate changes, then how do we actually proceed with uh, the deposition of the adsorbate? How do we actually proceed with the change in d orbital structure? All these are band gap variations, and these things have to be taken into consideration. So in order for the new materials to be either in application oriented physics or fundamental sciences, we have to understand the electronic structure of these materials and the electron phonon interactions, for example, and also the impurity and adsorbate interactions. There are certain properties which define how critical and robust a material is. When we are studying crystal structures, mostly we are going to see only about how atoms and molecules or atoms are arranged in a very periodic fashion. But before we study these kind of periodic structures, we have to understand what are some of the very defining characteristics or some of the important parameters that is going to define this periodicity or define a crystalline structure. There are certain parameters which we will consider here. Even though there are a lot of parameters, the most important things would be like the bond energy, the melting temperature, elasticity, and coefficient of thermal expansion. These are the things which we are going to see here. The bond length actually defines how stable a crystalline or any metallic structure is. If the distance between the two atoms or the molecules that makes the crystal becomes too big, then the interaction between them becomes meaningless. If they are too close, then it is going to become a Pauli repulsion, and whatever is happening between them does not again make sense. So the bond length makes a very important parameter. Then comes the bond energy. The energy between two atoms that makes a periodic structure should be very appropriate, and it has to be in the most comfortable and lowest energy possible. If the energy between the two atoms or in a structure is extremely high, the material is going to be very unstable, and if it is extremely low, the material can be easily pulled apart and does not have any intrinsic strength. The next property which we are going to see is the melting temperature. Before we see the melting temperature, we can see what this kind of graph means and how each of these parameters can be represented by a simple graph. We have an x and y axis. The x axis determines the length between or the distance between the two atoms, and the y axis represents the energy that is separating or attracting the two atoms. The bond energy is how far is the lowest energy the graph can go, and the bond distance is what is the lowest minima, which is in which the atoms are at a most comfortable position. So from the origin to the R0, which is unstretched length, would give us the distance between the atoms, and the lowest energy in the y-axis would give us a bond energy E0. If there are any kind of variations in this graph, we can determine what are the properties that are causing this variation. So, when we come to melting temperature, when the melting temperature is extremely small, then the bond energy is also small, which actually makes sense, because if the melting temperature is small, which means the material can be easily melted, then the energy between the two atoms or in a crystal structure is also extremely small. If we need a larger melting temperature, which means we have to give a lot of energy to melt the temperature, then the bond energy is also going to be higher. This is what we have represented in the x and y. If we extend this graph to understand a little bit more, as I said, the energy is represented in the y-axis, and the x-axis determines the distance between the atoms. So, if, for example, here we take the case of two hydrogen atoms, if the two hydrogen atoms are extremely close, the energy between them is too high. However, the energy does not touch any point on the y-axis, but it goes on and on until infinity. And when the distance between the two atoms comes to a nominal standpoint, it reaches a maxima or a minima if you see it the other way, and then as the distance increases, the graph goes towards zero. So when the distance between the two atoms is actually again too far, there is no energy between them and the energy reaches zero. Again, this graph does not touch the x-axis but keeps going on. We see the next parameter, which is the elastic modulus. Let's take the case of a cross-sectional or a cubic rod with a cross-section A0. It has an initial length of L0, and then we apply some amount of force in the x direction, and then the cubic rod is actually deformed to a length of delta L. The force applied with respect to the cross-sectional area 0 is certain times of change in length with respect to the original length, and this certain time represents the elastic modulus. So again, if the elastic modulus is small, the bond energy is also small, which again makes sense. If the elastic modulus is very high, which means the material can be pulled to a lot of extent without breaking it, then the bond energy is also extremely high. Now let's go to the next property, which is the coefficient of thermal expansion. We take the same case. We have a cubic rod with a cross section of x, y, whatever. It has an initial length of L0, and then this cross section is heated, and then the rod is changed in a certain shape, or if we consider only two dimension, in a certain length. This change in length is called delta L. So the change in length with respect to the original length is somehow dependent on how much temperature we give, and this certain time or certain amount is actually called the coefficient of thermal expansion. Again, we have to remember this is not temperature, but rather this is the coefficient of thermal expansion. However, the coefficient of thermal expansion is inversely proportional to the bond energy. So, when the coefficient of thermal expansion is larger, the bond energy is smaller, and vice versa. So, if we summarize all the three cases, in cases where there is a large bond energy, like ionic and covalent bonding, then there is a large uh, melting point, large elastic modulus, and a smaller coefficient of thermal expansion. In cases of metal, the cases are always averaged out because the bond energy is variable. Not all periodic structures in a metal have a very predictable bond energy. So the melting temperature, elastic modulus, and the coefficient of thermal expansion is actually averaged out. In polymers, again, the cases are directional, and instead of primary, the secondary bonding starts to dominate, and it is actually the inverse proportion of ionic and covalent bonds, which means the melting temperature and elastic modulus are small, sorry, and the coefficient of thermal expansion is high. Now we see certain types of solids. These are some things which we have seen in high school, but here we are going to see it in a little bit more detail. So what are solids and how are they basically classified into? Solids are basically classified into crystalline or polycrystalline or amorphous. Crystalline structures are very equally spaced and periodically repeatable. And this, instead of saying just crystals, we could say single crystal, because single crystals are something which we are going to use for a large different classes of experiments. Single crystals are now most commonly used in a lot of physics labs, and also for battery oriented applications, for catalysis, for even for corrosion. So, a single crystal is a very regular and repeatable periodic geometry, and throughout the material, the crystalline structure exactly remains the same, with no change in bond energy and no change in the distance between the atoms. The second type of crystal is a polycrystal. Polycrystals are somehow very similar to single crystals, only that there are different zones of crystals which exhibit a different direction of repetition. However, it's not a different crystalline structure, but only a different uh, it's only a different direction of periodicity. The distance between the atoms remains the same. The energy or the bond energy also remains the same in most cases, only that the direction is in a different zonal way. Amorphous structures, as you know, does not have much order, but they also have a very potential use in certain kinds of semiconductors or even power lines. Some of the power lines and semiconductors are absolutely necessary to be amorphous, and even if we have a nice crystalline structure, it's not going to be useful in these kind of applications. So amorphous structures have their own applications, but it doesn't have any kind of periodicity or regular representation. Again, if we summarize these kind of materials with respect to the energy diagram which we have seen before, what do we understand? In a crystalline structure which is dense and regularly packed with unequal periodicity, there is a more comfortable and lower energy point which is represented here, and it is at this point the crystalline structure is most comfortable. Again, the distance between the atoms tend to be lower on an average, whereas for a randomly oriented structure, the distance from the origin to the point of reference is a little bit higher, but at the same time the energy is also higher, which makes it a little bit more unstable. So, since the whole concept is about metallic crystals, today we'll concentrate more on metallic structures rather than organic or inorganic structures. What are metallic crystals? Metals in most cases are represented in a crystalline structure. Metals are naturally crystalline except certain amount of metals like mercury, for example. But any metal that tends to be a crystal is usually densely packed and have extremely regular periodic structures. And there are several reasons for this dense packing. Usually only one element is present. Mostly in the bulk of a metal there are no impurities. Typically there should be no impurities. Only one element is present. So all the atomic radius are the same. When all the atomic radius are the same, it is very easy for the metals to come together and share electrons with each other. When they start to share electrons, a bond is formed and the bond becomes extremely strong. At the same time, a metallic atom is surrounded by other metallic atoms on all sides, and it is easy for the metal to share electrons with the atoms on all sides. So the structure is also not actually directional, but the nearest neighbor distance is very small, almost overlapping, and this is one of the reasons metals are extremely strong. The thing is, when the nearest neighbor distance, which is the adjacent atom, is actually very small, the atom does not need excessive amount of energy to form a bond with them. So naturally, the bond energy is lower. And usually, metallic crystals are represented only in certain types of structures like body-centered cubic, face-centered cubic, and hexagonal close pack. These are some things which we are going to see in detail. So, what exactly is an ideal crystal? An ideal crystal is a periodic array of structural units, a repetitive unit such as atoms or molecules. It can be constructed by infinite repetition of these identical structures or structural units in any amount of given space. The structures can be described in terms of a lattice. This is the most important concept which we are coming. A lattice is something which is a very small repetitive unit of a crystal structure. And the group of atoms that forms the lattice is called a basis. So, if we see what is a lattice in a little bit more detail, the periodic arrangement of atoms in a crystal is called a lattice. By replacing each group of atoms by a representative point, a crystal lattice is obtained, which means any kind of repetitive structure that we are using, or when it happens to get a repetitive structure to complete a crystal, is called a lattice. The lattice doesn't have to be only an atom. A lattice point can be a group of atoms or even a quantum dot, anything that we try to obtain. This combined lattice point is called this combined lattice point is called side structure, but straight structures are somehow different. I'll come to that point later. What at this point we have to remember is any kind of representative repeatable unit is called a lattice, and the point with which we seek representation from a lattice is called a lattice point. Lattice actually starts with a unit cell. And what is a unit cell? Unit cell is actually the smallest volume of the crystal. And if this smallest volume is actually repeatable, and if we could repeat it to get the entire crystal structure, this we call the unit cell. For example, in the first structure, you can see a rectangle which is tilted at a small angle of 10 or 20 degrees. The most smallest repeatable unit that we can obtain here is a rectangle which is slightly tilted. In the second structure, we see a rectangle which is just 90 degrees between them. However, in the third structure, you will see a small difference. There is a rectangle and there is also a four-sided structure which is tilted at an angle away from the rectangle. And the smallest repeatable structure in this third structure can either be a rectangle or an angular four-sided structure. Both of these things actually form a primitive cell. This primitive cell in certain cases is called a unit cell. In the fifth structure, it's a hexagonal structure, and the hexagon is the smallest you can obtain. You cannot go any smaller than the hexagon, even though you can go into a kind of four-sided structure. It will not be enough for representing the whole of the crystal. So the hexagon is the smallest structure in the fourth case, and the square is the smallest structure in the fifth case. This is called a unit cell. Now let's go to the next concept. I am just introducing these concepts because these are actually the parameters with which we will be able to represent a crystalline structure. Anyway, the next concept is called the translation of vectors. What is a translation of a vector? It's a very simple concept. If we want to represent a certain amount of atoms, if we want to indicate a certain amount of atoms, it is just enough to say in a two-dimensional structure that is it is at a certain distance from a point of origin, and again in a different direction it is at a certain distance, and again if you go to the y-axis it is at a certain distance. This actually gives us the original uh, point of need. So in the diagram which you see here, we can see in the x-axis there is only a one atom translation. Again in the xy axis there is a three atom translation, which is two adjacent atom translation, and again a two adjacent atom or a three atom translation in the x-axis. So how do we represent this? One atom in the x-axis, two atoms in the xy axis, and again one atom in the x-axis. If we have to represent this in a vectorial way, we can say that a certain amount in the A1 direction plus certain amount in the A2 direction and certain amount in the A3 direction. This certain amount is actually a scalar which represents only the magnitude, and the direction which we call A1 vector, A2 vector and A3 vector is actually a vector which represents the direction which we desired. Apart from the direction, if we can also tell the angle between these two vectors, it will give us exactly the precise point at which atom we are going to desire. Next we come to the concept of primitive vectors. In the first diagram, what you see is a two-dimensional lattice representation. How do we actually represent each point here? It is just enough to say A vector and B vector. Let us say we take one atom here, any one atom as a reference point. From this reference point, if we have to point out any other atom, we can just use these two vectors and the angle between them. So that gives us only three variables. So from one reference point, if we have to go to the other reference point, we can say it is 4 or 5 times of A, 6 times of B, and a 30-degree angle between them, for example. This will give us exactly which kind of atom we are targeting from a reference point. This is all well with a two-dimensional structure. What if we are dealing with a three-dimensional structure, which is usually the case in a normal crystal? Again, there we can just use a normal convention such that a vector points towards a certain direction. Let's say that the vector A points towards the x direction, B in the y direction, C in the z direction. Again, we need only 6 parameters to represent any point in a three-dimensional crystal. So, what are these 6 parameters? The length of the vectors and the angle between them, which we call A, B, and C, and alpha, beta, and gamma. With these 6 points, any space or any reference point in a three-dimensional crystal can be represented. This way of representing and the vectors involved here is called the primitive vectors. So if we have to summarize, we have primitive and non-primitive vectors. In a primitive vector, we have only a single lattice point per cell, but in a non-primitive vector, we have more than one lattice point. If we see in this diagram with the blue balls, this unit cell, which is represented by the blue structure, cannot be made any more smaller. So that would be a primitive cell. But in a non-primitive cell, this is not the smallest structure. The red ball, the body-centered cubic, for example, represented by side A, can be made into even more smaller structure, but it would not make much sense. That would be called a non-primitive cell. Okay. Now, so far what we have seen is only very small structures in an atomic level. What if we go to the bulk structures? In a bulk structure, if we keep on dividing and going into smaller and smaller pieces, at some point we cannot divide the bulk anymore. The bulk would actually come to a standstill. It would come to a point where we cannot decimate it, or where we cannot divide it even anymore. And what are we going to do at this point? The point at which a bulk cannot be divided anymore in a three-dimensional structure would be called a unit cell in 3 dimension. Or in other words, we can also say if we have a 3-dimensional unit cell, this can be constructed upon to get a bulk structure which finishes the whole crystal. And what are the types of bulk crystals which we can get in nature, which is most commonly expressible, which is most commonly available? There are basically 4 types of solids, 4 types of bulk, which we call symmetry. The 4 types are orthorhombic, tetragonal, cubic, and hexagonal. The orthorhombic does not have equal sides, but the angle between them is very sharp. It's 90 degrees. In a tetragonal structure, it is also divided at an angle of 90 degrees between all the sides. However, 2 sides are equal and 1 side is not equal. A cubic structure, as the name represents, is a perfectly symmetrical structure with all the sides equal, A, B, and C, and the angle between them 90 degrees. In a hexagonal structure, only 2 sides are equal, the third side is not equal, and again, only two sides have an angular separation of 90 degrees and the third side does not have an angular representation of 90 degrees. There are some elements that are naturally occurring. For example, tungsten dioxide is orthorhombic, amethyst is tetragonal, pyrite is cubic, and aquamarine is hexagonal. What are these symmetries like cubic, orthorhombic, tetragonal, what we saw? All these structures belong to a bigger class of crystalline representation called the Bravais lattice. The Bravais lattice is a distinct type of lattice, and every type of crystalline structure falls under the Bravais lattice at some level. Or we can even go to the extent of saying every kind of space that can be filled in the entire universe can be fit into some kind of Bravais lattice. One or the other kind of Bravais lattice is going to fill up the entire space. That is the whole concept. The four symmetries which we saw before, like orthorhombic, tetragonal, cubic, and hexagonal. Apart from this, there are a few other types of Bravais lattice, which is triclinic, monoclinic, rhombohedral, and so on. Together, there are 14 types of Bravais lattice that is going to fill up the entire crystalline structure. How do we identify a Bravais lattice? There are four very important parameters. Each of these unit cells of the 14 Bravais lattices, they should exhibit one of these following symmetries. Either it should have a reflection symmetry, which means the reflection of a structure across a plane. If we keep it in front of a mirror, the reflection should make some sense where you will be able to take notes and how you will be able to measure the direction and the length of the vector uh, by using this parameters you obtain from reflection. Or it should have a symmetry that is obtained by rotation. For example, if you rotate it a little bit, it won't be symmetric, and if you rotate it 180 degrees, it may become symmetric. That is a kind of symmetry. Or it has to be symmetric by inversion, which changes the sign or which changes coordinate. However, if you rotate it again, inverse it again, it will come back to the original position and become symmetric. The center of symmetry will be an inversion point. And the fourth one is called an improper rotation, which means there is a rotation and then followed by an inversion. If any one of these following 4 points are satisfied in a crystalline structure or a crystal material, then it falls under one of the 14 Bravais lattices. Then we actually come across a lot of different types of crystals. However, only 3 types of cubic crystals are very, very important. Or this is a kind of crystalline structures which we use in day-to-day life in a lab scale, which is face-centered cubic FCC, body-centered cubic BCC, and hexagonal close packed structure. It's not a cubic structure, but still broadly classified in this way because of ease of representation. Before we see what are these BCC, FCC, and HCP, we will go to understand one important concept called the atomic packing factor. What is an atomic packing factor? It is basically a very simple concept. How many atoms are packed inside a specific structure, which is hexagonal close pack or a rhombic structure? Basically, how many atoms are packed inside a given volume? That is called the atomic packing factor. So, we have to consider the volume of atoms in a specific unit cell with respect to the volume of the total unit cell. Here, the atoms are usually considered to be a sphere. For example, the formula for finding the atomic packing factor is the number of atoms multiplied by the volume of the sphere 4 by 3 pi r cube, where r represents the radius of the sphere, divided by the volume of the unit cell. How do we calculate the number of atoms? First, we take the unit cell. In the given example, there is a cube and you see 1/8 of an atom, and every corner has 1/8. So there are totally 8 1/8 atoms. That becomes one atom. That is what is represented here. And then the volume of the sphere, where we can just calculate the radius, which is 0.5 times of A is side of the cube, divided by the volume. Volume is just A cube into, if it is a simple cube, and if it is not a cube, the volume is not such a difficult thing to calculate. The atomic packing factor actually determines how dense or how neatly or tightly packed a crystalline structure is. It is not the same as density. Density is slightly a different concept, but in a unit cell, how tightly the atoms are packed is given by the atomic packing factor. Let's then go back to the three structures FCC, BCC, and HCP. What is a face-centered cubic? The face-centered cubic, as the name indicates, there is a face in the center. This is very simple. Atoms are located at the corners and on the center of the face. Here, in this structure, which is in the last right, you will see the radius is 4r, or the diagonal is represented by square root of 2 multiplied by a, which is the side of the cube. There is a full face of an atom in the center and 1/8 of an atom on each corners. Many common metals like copper, silver, nickel, and lead have this kind of FCC structures. And the FCC can be represented in various ways. Usually, it can be represented by a complete ball structure or a ball and stick structure. If you see this structure where uh, the complete FCC is given, you can see all the four corners where 1/8 of an atom is placed and all the centers where a complete half face of the atoms is present. So as I told in the previous slide, from this it is easy to calculate the atomic packing factor. But we'll see a little bit more about the FCC. The atoms are the corner of the unit cell and the center of each face. So therefore, there is totally 4 atoms. You may think about it how we get 4 atoms. So we have 4 atoms in a unit cell of an FCC. If we have to calculate the primitive vectors of the FCC, we can choose the in-between points here, here, and here in the face of the FCC. This can be represented by A1, A2, and A3 vectors in the X, Y, and Z direction. Here, since A1, A2, and A3 are in the center, this we can represent as A divided by 2 multiplied by X vector plus Y vector. This is the basic convention of the vector representation, as I told before. Similarly, A2 can be represented by a combination of X and Y vector, and A3 can be represented by a combination of X and Y vectors. A face-centered cubic would belong to one class of a Bravais lattice. How do we calculate the atomic packing factor of an FCC? As I said before, there are 4 half atoms in the center. There are 6 half atoms in the center. So 6 multiplied by 1 half, plus there are 8 1/8 atoms at the corners of the unit cell. So 8 multiplied by 1/8. That becomes 4 and multiplied by the volume of the sphere divided by A cube. So if we calculate this, the atomic packing factor of a face-centered cubic would become 0.74. It does not have any units, it's a number. Some basic info about the face-centered cubic. The hard spheres touch along the diagonal, as I said before. The edge length A is 2 times multiplied by radius multiplied by square root of 2. The coordination number, which is actually the number of closest neighbors, is equal to the number of touching atoms. This means the coordination number for an FCC is 12. The number of atoms per unit cell is 4, as I have calculated before, and the atomic packing factor is 0.74, and I have told you how to calculate the atomic packing factor. The best example of a face-centered cubic is common salt or the NaCl structure. The NaCl actually becomes a crystalline structure. It crystallizes into a cubic lattice. Equal number of sodium and chlorine ions at alternate points form this FCC structure, and each ion has 6 of the other ions as its nearest neighbor, whether you take sodium or chlorine. Next, we come to the body-centered cubic, or the BCC. The BCC has two lattice points and is not a primitive cell, it's a non-primitive cell. It has 8 nearest neighbors. Each atom is in contact with its nearest neighbor only along the body diagonal planes. You will see what I mean by this in the next two slides. Usually, alkali metals are naturally formed as body-centered cubic crystalline structures. How do we calculate the primitive vectors of BCC crystals? Again, the BCC structure extends into all the directions, so it is in the x, y, and z directions, but also in the positive and negative spheres. So, the A1, A2, and A3 vectors, which we say is A1 vector is divided by 2 because it is in the center, and it can be represented by x, y, and z axis. Whether it is positive or negative is something which cannot be explained here, but if we have a paper and pen, we can see which is, if it is in the positive x direction, we can call it as plus x. If it is in the negative x direction, we can call it minus x. And with this, we can calculate a divided by 2 multiplied by a combination of x, y, and z vectors. The body-centered cubic structure has a coordination number of 8, and the close pack directions are cube diagonals. So the diagonal would be 4r, and it would be, or it could be represented as square root of 3 multiplied by a. In the previous FCC structure, the 4r was represented by square root of 2 multiplied by a, and here we have square root of 3 multiplied by a. How do we calculate now the atomic packing factor of a body-centered cubic? Again, there is one whole atom in the center, plus there are 8 atoms. That becomes 1. So together it becomes 2 multiplied by volume of the sphere divided by the total volume. And the atomic packing factor can be calculated this way for the BCC, which becomes 0.68 with no units. Some basic info about the BCC. Hard spheres touch along the cube diagonal, and the cube edge length A becomes 4 multiplied by r, which is the radius, multiplied by divided by square root of 3, or we can say 4r is equal to square root of 3 multiplied by a. The coordination number is 8, and the number of atoms per unit cell is 2. The center atom is not shared, it is a completely big ball in the center, and the corner atoms are shared, and the corners are filled with 18 atoms. The atomic packing factor becomes 0.68, and the corner and the center atoms are equivalent both in properties and the size. Next, we come to the hexagonal close pack. As the name indicates, the hexagonal close pack is a very hexagonal structure on 2 layers, and interestingly there is another in-between layer which has only 3 atoms. The 2 layers which forms the hexagon has 6 atoms, and the in-between layer, which is called the B site, is having only 3 atoms. Very famous crystalline structure which are commonly used in single crystal physics, like cadmium, magnesium, zinc, and titanium has this kind of crystal structure. They have a very unique d orbital structure. The d orbitals are not completely adjustable. They have a very complicated pattern, and the d orbitals are actually tunable and tailorable whenever we deposit and adsorb it. And because of its tunable nature of the d orbital, the hexagonal close pack are the most commonly used crystal in crystal physics. It has a coordination number of 12, and we can see a 2D projection. It's already getting complicated, where the first and the third layers are completely overlapping on top of each other, and the in-between layer, represented in blue, has only 3 atoms which is projected on top. In case of a hexagonal closed pack structure, there is something only very important point which we have to remember. This is hexagonal closed pack is not a Bravais lattice. There is a lot of gap in the hexagonal closed pack because of two uneven and unequal structures embedded in between. This unevenness actually disrupts the d orbital bonding, which is not the case in BCC or FCC. There the d orbital is completely homogeneous, which is not the case in HCP. However, interestingly, most of the metals which are interesting and used on a lab scale or even in industrial scale are formed as hexagonal closed pack. Some parameters for HCP are the coordination number is 12 and the atomic packing factor is 0.74. The rest of the details as mentioned previously. We saw the atomic packing factor. However, the density of a metal or a crystalline structure is something very different from the atomic packing factor. As I said before, the atomic packing factor comes into play only when we are talking about a unit cell. However, in a practical sense, the density of a material in square millimeters or square centimeter or in a volume scale becomes important in practice. For example, the density is also very different in several metallic structures. For example, lead and gold are very dense, aluminum, cadmium are not that much dense, and so on. How do we calculate the density? The density of the material, or if we calculate density of even a unit cell to be more precise, the density of a unit cell is the number of atoms in a unit cell multiplied by the mass divided by the volume of the cell. And the volume of the cell also includes Avogadro number, which we have learned in high school. So, if we want to calculate the density of a material at a very small scale, we can compete it with the atomic packing factor, even though these are two different concepts. For a unit cell, interestingly, both atomic packing factors and the density can be calculated separately. However, density becomes more, we have to remember density becomes more important when the size increases, when the material becomes more practically viable or transferable. But on an atomic scale, atomic packing factor is a more important concept. So, the density of a material can be calculated by these parameters, the number of atoms multiplied by the mass of the atom divided by volume of the cell multiplied by Na, which is the Avogadro number. The volume of the cell is just A cube in face-centered and body-centered cubics, and the side would be 2 times multiplied by the radius multiplied by square root of 2, and the side for a BCC would be 4 times of the radius divided by the square root of 3. The atomic weight and atomic radius of elements are in the table in many of the textbook covers or even in any periodic table structure. We can use the same values to calculate the density and the atomic packing factor. So, hexagonal closed pack is the only structure that is very unique in this whole list of things. FCC, BCC, or cubic, tetragonal, and other structures have a kind of predictable pattern, which is when there are overlapping structures, there are no gaps in between. If there are no gaps in between, what that means is the d orbital bonding is homogeneous. However, the d bonds and the homogeneity goes for a toss in HCP. This makes the structure extremely unique, and these unfulfilled spaces give rise to a lot of interesting electronic structure when there are organic and inorganic adsorbates, or even if we are depositing some other metals on top of the HCP metal. So HCP disrupts the d orbital stacking and it has empty spaces. However, the binding is much stronger in FCC and BCC. This actually brings to the end of the normal kind of lattice structures or the crystal structures. There is one more kind of important crystal structure which I would like to mention. I could not go into detail of this. It is called the Wigner-Seitz cell. The Wigner-Seitz cell I can give only an introduction. The detailed analysis of Wigner-Seitz cell requires a lot of quantum mechanics, and hence I would not go there. But what is a Wigner-Seitz cell? It is a simple way to find the primitive cell in a 3 dimension. So we just have to choose a lattice point, and we have to draw lines to connect all these lattice points to the neighbors. At the middle of all these lines, we draw another plane or a line which is actually 3 dimensional. So this is going to cover the entire reference point or the initially chosen lattice point. This covered up area is called the Wigner-Seitz cell. For example, in a 3 dimensional structure, it would look something like this. And this is extremely important in a lot of K-point analysis and variation in electronic structure after an adsorbate is deposited on a lattice structure. However, I would like to not go into detail about the Wigner-Seitz cell. I just want to give you an introduction. So this brings us to the end of the lecture. I hope I was able to introduce a lot of familiar and unfamiliar points in the crystal structure and crystal physics, which will be useful for us to solve basic problems and understand some of the fundamentals of crystallography. So, thank you for the opportunity. And if you have any questions, it can be mailed to the following email address. Thank you.